Everyone, my name is Nikhil Mehta, and I'll be talking about HyperMix, out of distribution detection, and classification in few shot settings. This is joint work with Kevin Liang and my colleagues at Mehta. I'll talk about few shot OOD classification and detection. For few shot classification, our goal is to classify a given query image into novel classes where a few labeled class examples are provided. For out-of-distribution detection, our goal is to detect samples at test time that are far from the training distribution. In this work, we'll study both few-shot classification and out-of-distribution detection under one setting. So our problem setting is as follows. Given an episode of n-way k-shot examples with q query examples, our goal is to perform n-way classification of those q query examples, where only k-labeled support samples per class are provided. We have to first detect if a given query is from out of distribution or not. If query belongs to in distribution, then we'll perform n-way classification for the given query example. So the training for few-shot classification happens in two phases. First, we pre-train a model to predict class of the given image using all the classes in the training set. Then we have the meta training stage, where we train a classifier on top of the backbone of the pre-trained model on n-way k-shot classification tasks, which are sampled from the training data. And during testing, we test the model on unseen n-way k-shot classification tasks. The provided query examples may not belong to any of the n classes in the episode during this testing phase. So the contributions of this work are as follows. We first empirically showed that the current state-of-the-art OOD methods have limited success in the few-shot learning scenario. In fact, the naive maximum softmax predictive probability detector was more reliable than other OOD methods for few-shot settings. Next, we propose a hypernetwork framework called HyperMix that uses Mixup for query and support set augmentation that strongly outperforms baseline methods in a variety of few-shot OOD settings. So the first approach is ParaMix. ParaMix enables support set augmentation for hypernetworks using Mixup augmentation. So as shown in this figure, on the left, we first perform mixup of various support samples in our support set. Then we extract the embeddings using the feature extractor backbone. Then we generate weights, the classifier weights, from the hypernetwork architecture. These weights are then aggregated based on per class label weighting. This is determined based on the lambda that was used during mixup. After aggregation, we get the classifier weights, which are then used to classify the query examples. The second component is the query set augmentation. We perform out of episode mixup, where during training we mix in episode and out of episode samples to improve the robustness of the model. We experiment with this approach on various few-shot benchmarks. We measure the in-distribution accuracy, and for OOD detection, we look at AUROC and FPR90. Under various settings, we find that HyperMix outperforms many of the few-shot and OOD detection baselines. We not only improve the OOD detection in few-shot setting, we also see that HyperMix improves the in-distribution accuracy compared to baseline protonet and hypernetwork architectures. We also experimented on noisy versions of these few-shot benchmarks, where we introduce varying levels of label noise in the support set. As shown here, HyperMix again significantly outperforms most of the OOD detection baselines in few-shot, noisy few-shot setting. We also see that few-shot accuracy on these benchmarks was consistently higher for HyperMix with varying levels of label noise in the support set, as shown in these two plots on the right. Thank you. Please visit us at our poster if you are interested to know more details about this work.